Let's do another example. Let's calculate the integral of z plus 1 over z cubed over gamma, where gamma is going to be the ellipse determined by z minus I plus z plus I equals 4 traversed counterclockwise. Okay, so this is going to be, if you wanted to actually graph it, this is going to be, it'll look something like this. And then we're going to go counterclockwise. So it has focal points I and minus I, and that's fine. That's good enough for me. So we want to calculate this integral. This integral does not have a derivative everywhere inside. So it's not defined at 0. Okay, so we have to be a little bit careful about that. So this integral is not going to be 0 necessarily right away. We have to do a little bit of work. But what we can do is we can actually cube what we get here. So this is going to be the integral over gamma of, let's see, z plus I over z cubed is going to be z cubed plus 3z plus 3 over z plus 1 over z cubed, just by cubing everything. And we're going to do the usual trick, as you guessed. The only place where we have to be careful is at the origin. So we can continuously deform our path into whatever path we want. And we've already seen that when you have 1 over z, or in this case 3 over z, the unit circle is going to work great. Actually, any circle of any radius is going to work great. And so let's translate this and let's write this as the integral over, let's say, gamma naught of z cubed plus 3z plus 3 over z plus 1 over z cubed dz, where gamma naught is, gamma naught of t is going to be e to the it. So gamma naught is the unit circle traversed counterclockwise. So e to the it, where t goes between 0 and 2 pi. Okay, and what we could do is we could plug everything in and evaluate, but that's kind of a pain. So what I want you to notice is that this is going to be the sum of 3 integrals, and I'll explain why I have to do 3 integrals in a second. Oops, this is the sum of 3 integrals, and it's the integral of z cubed plus 3z plus 3 times the integral of 1 over z plus the integral of 1 over z cubed dz. Okay, and so let's give ourselves just a little bit more room here. But these are the 3 integrals that we need. Notice that z cubed plus 3z is a polynomial, and therefore it's entire. And therefore, since gamma naught is a closed curve, this integral is 0. So this integral is 0 by the second corollary to Cauchy's theorem that we talked about. It's an entire function integrated over a closed curve, so it's 0. The integral of 1 over z over the unit circle we computed before. That's 2 pi I. So we're going to multiply by 3. That'll give us 6 pi I. And therefore, the only integral that we'll have to evaluate is 1 over z cubed over the unit circle. And we'll have really no choice but to go through and do the definition here. This function is not holomorphic over, we have to be really careful about the origin. The fact that the origin is inside the curve matters a lot, because that means that we're not allowed to translate, we're not allowed to come up with a second homotopically equivalent curve that excludes the origin. The origin has to stay in there because really we're working over the set, even though this was not explicitly talked about. The underlying set that we're thinking about is the complex numbers minus the origin, because our function is holomorphic on that set. Okay, that's really the largest set where the function's holomorphic. But we have to be careful about the origin. Okay, so that's kind of the underlying fact there. So let's evaluate what this integral is. So let's actually do this off to the side, and we'll just come back up. So this will just be some side work here. But the integral over gamma naught of 1 over z cubed is going to be 1 over e to the it cubed, right? Because we're going to take f of gamma. So it's going to be take gamma, plug it in to our function. So we're going to get e to the it cubed. times the derivative of gamma, which is going to be I e to the it. And we're going to integrate from 0 to 2 pi. Okay, and so this is going to end up being, you can bring the I out, the integral from 0 to 2 pi. And then we're going to have, once you simplify this, this is e to the minus 2it dt. And then, therefore, when we integrate, we're going to end up with I times, let's see, e to the negative 2it divided by negative 2it, or divided by negative 2I. And we're going to evaluate from 0 to 2 pi. And this is going to be some constant, so in this case, negative 1/2, e to the negative 4 pi I minus e to the 0. So minus e to the 0. And both of those quantities will be the same value. They'll be 1. And therefore, this integral is going to end up being 0. So it turns out that our entire integral that we were looking for before is going to be 6 pi I. Okay, so 6 pi I. And again, we split this up and we use different theorems for different parts. So notice that for the first part we used, just to take a step back, we actually used Cauchy's theorem twice. We did a lot in this example. We first used Cauchy's theorem and we found a homotopically equivalent curve gamma naught, so that these will give us the same integral. So that's perfectly valid. Everything is good. Then we use the corollary to Cauchy's theorem that since z cubed plus 3z is a polynomial, therefore it's entire in the entire complex plane. And if we integrate over whatever closed curve we want, we'll get 0. This middle integral we evaluated many times before. That was actually one that we did just in the previous video. So that was 2 pi I, and then the times 3 makes it 6 pi I. And then the final one, what ended up turning out to happen is that 1 over z cubed has an antiderivative in this region. So 1 over z cubed has an antiderivative in that region, and it's continuous in that region. And therefore, you can use the path invariance theorem so that if you have an antiderivative, the integral over a closed path is 0. Notice that 1 over z does not have an antiderivative on this entire region because you have to be very careful about what happens. So here's your complex plane. You have to be very careful what happens over here on the negative real axis, right? There's problems there. We've talked about that. That's why we have to do branch cuts. And so this does not have an antiderivative on that region. Therefore, we have to use the definition. But when we put all the pieces together, this integral turned out to be 6 pi I.